Right. So I'm just going to throw this in as on the last question here. So it says show that the basis set of S, this same set here. Okay, show that this set that the basis set is not unique. In other words, could we find another basis for this set S? Okay. So notice that in this situation, we set in the vectors v1, v2, v3, v4, v5. Okay, to show that this is not unique, that the set of basis vectors that we chose, because remember, it's a linear combination. So as long as we can find any example of this, one way to do this, probably the easiest, is just to rearrange the vectors in the uh, coefficient matrix. Just rearrange them in a put them in a different one. A simple one could be like count backwards, right? So what if we did v5, v4, v3, v2, v1. Okay, so if you can imagine making this our coefficient matrix A, okay, so our A would look different. We would have literally this is like flipping it over, right? So it'd be 5, 4, 3, 2, 1. Okay, that's what this matrix is doing. Okay, if we did that, okay, if we wrote it in this form, this matrix A, and we did the row reduced echelon form, what we would find is that that vector 3 would be written as negative v5 plus v1, v4. So this matrix, which is another way of saying just changing the order of these things here, right? That V3 could be written as a linear combination of these two. Okay, likewise, V1 in this case actually becomes a linear combination of V2, and it's written as negative 1/3 V1. Okay, so V2 or V1 is written as a linear combination of that should be a V2 here, so I meant to try to squeeze in V1 in. So V2 is the independent vector, and V3, V2, 1 equals the, let me start over and see if I can say that in a clear way. So V1 is a linear combination of V2, where V1 is equal to negative 1/3 V2. Okay, so here we have again we'll have two rows of zeros here in the reduced row echelon form of this matrix, and the linear combinations we get will be V3 is equal to V5, a negative V5 plus V4, and we'll get that V1 is equal to negative 1/3 V2, which means that our basis set that spans the space here we had we had V1, V3, and V4. Here we're going to find that the basis set is now going to be, so the basis would be V5, V4, and V2. Okay, so the sets have changed by writing it in reverse order. I think it's helpful to see that. So let me summarize this. So S with V1, V2, V3, V4, V5. Okay, so this augmented matrix led S to have the basis set of V1, V3, and V4. So those vectors form the basis when we put them in order as in the original problem. When we change the order, so V5, V4, V3, V2, and V1, when this was our A, okay, then this led to S having the basis set of V5, V4, and V2. Okay, so the basis set changes depending on the order of the written vectors that make up the coefficient matrix. Okay. However, both sets are linear combinations of each other. And what I mean by that is we can write V2 in terms of V5 and V4, or we can write V5 in terms of V3 and V4. Okay, so however we choose to form the basis set, they're all linear combinations of each other, which is why the basis sets are not unique. They're all going to be linear combinations of each other. they're able to span that space, and so they're going to be written as linear combinations of each other. I know I keep saying that, but it's really important to understand that. So I hope that makes sense, and I'll see you in the next video.